Betelgeuse is a star so colossal and enigmatic that it seems to defy the very laws of physics. The massive red supergiant in the Orion constellation, just 650 light-years away from Earth. Recently, this star stunned astronomers with its bizarre rotational speed and unexpected dimming, sparking wild speculations of an imminent supernova. But Betelgeuse's mysteries don't stop there. What could be causing a star of such immense size to spin at such breakneck speeds? Is it cannibalizing a companion star? Or are we witnessing an unprecedented cosmic illusion? Stay with us as we uncover the intriguing secrets of Betelgeuse and explore why this stellar giant looks a lot stranger than we ever imagined. Betelgeuse, a red supergiant star in the Orion constellation, has fascinated astronomers and stargazers for centuries. Located approximately 650 light-years from Earth, Betelgeuse stands as the second largest and 10th brightest star in our night sky, excluding the Sun. With an estimated diameter about 1,400 times that of the Sun, Betelgeuse is so large that if it were placed at the center of our solar system, it would extend beyond the orbit of Jupiter. The star's name, derived from Arabic, means the hand of the giant, reflecting its prominent position in the constellation of Orion, representing the hunter's shoulder. Betelgeuse is classified as a red supergiant because of its cool surface temperature, around 3,500 degrees Celsius, which gives it a distinctive reddish hue. In recent years, Betelgeuse made headlines due to its unprecedented dimming. In late 2019 and early 2020, the star's brightness dropped significantly, sparking speculation that it might be on the verge of exploding as a supernova. Such an explosion would be visible from Earth even during daylight and would shine as brightly as a full moon for weeks. However, this dramatic dimming puzzled scientists. Initially, it was thought that Betelgeuse might be undergoing changes in its internal structure or shedding significant amounts of material, forming dust clouds that temporarily obscured its light. More recent observations suggest that massive convective cells on its surface could be causing these fluctuations in brightness by altering the star's temperature distribution. Betelgeuse's potential to explode as a supernova has intrigued astronomers. When it eventually does, the explosion will release an immense amount of energy, momentarily outshining entire galaxies. The last time a supernova was visible to the naked eye was in 1604, known as Kepler's supernova, in the constellation Ophiuchus. Betelgeuse is nearing the end of its life cycle. As a massive star, it has burned through its nuclear fuel at an extraordinary rate. Currently, it is in the late stages of fusing heavier elements in its core, a precursor to the supernova phase. When Betelgeuse finally explodes, it will leave behind a neutron star or possibly a black hole, depending on the remnant mass. The star's imminent fate, combined with its recent dimming, has made Betelgeuse a prime target for observational campaigns. Instruments like the Hubble Space Telescope and the Very Large Telescope, VLT, have provided unprecedented details about its surface and surrounding environment. These observations are crucial for understanding the life cycles of massive stars and the processes leading up to supernovae. If you're liking the video so far, you should consider subscribing to the channel and help us create better content and reach more explorers out there. Now back to the video. Betelgeuse's recent behavior has defied our expectations, especially regarding its rotational speed. Observations using the Atacama Large Millimeter Submillimeter Array, ALMA, have revealed that Betelgeuse is rotating at a staggering rate of approximately 18,000 kilometers per hour, or about 5 kilometers per second. For a star of its size, this is 10 times faster than what current stellar physics would predict. To measure this, astronomers relied on the Doppler shift, a phenomenon where the frequency of light or sound waves changes relative to an observer's position. The Doppler shift is why a siren sounds higher-pitched as it approaches you and lower-pitched as it moves away. Similarly, as Betelgeuse rotates, one side of the star moves towards us while the other moves away. This movement causes a shift in the star's light spectrum. One side appears slightly bluer, moving towards us, and the other slightly redder, moving away. Using ALMA, astronomers could detect these subtle shifts in Betelgeuse's light. By analyzing the differences in the spectral lines, they concluded that the star's surface is spinning at a rate that seems physically impossible for a red supergiant. Normally, larger stars rotate more slowly. For instance, our Sun rotates at about 2 kilometers per second, a rate proportional to its size and mass. If the Sun were to expand to Betelgeuse's size, its rotational speed would decrease significantly to conserve angular momentum. In contrast, Betelgeuse's rapid rotation suggests an anomaly. One theory is that Betelgeuse gained this angular momentum through a process called stellar cannibalism. This occurs when a star in a binary system pulls material from its companion, absorbing not only its mass but also its angular momentum. If Betelgeuse once had a companion star, it might have stripped it of its outer layers, increasing its rotation speed beyond what is typically possible. Another hypothesis involves the star's turbulent surface. Betelgeuse is known for its massive convective cells, regions where hot plasma rises and cooler plasma sinks. These cells can create localized motion on the star's surface that might mimic the effects of rapid rotation. If these convective motions are mistaken for overall rotation, it could explain the unexpectedly high velocity readings. Moreover, Betelgeuse's rotation could be affected by its complex internal dynamics. As it nears the end of its life, the fusion processes in its core, and the resulting changes in mass distribution might influence its rotational characteristics. Angular momentum is a fundamental concept in physics that describes how an object's mass, shape, and rotational speed are interconnected. When an object spins, it has angular momentum, which remains constant unless acted upon by an external force. This is why, for example, a figure skater spins faster when pulling in their arms and slower when extending them. It's all about conserving angular momentum. For stars, the same principles apply. As a star expands, its rotational speed should decrease to conserve angular momentum. Imagine our Sun suddenly swelling to the size of Betelgeuse. To maintain angular momentum, its rotation speed would drop significantly. In fact, calculations show that if the Sun were the size of Betelgeuse, its rotational speed would be around 0.2 kilometers per second, drastically slower than its current rotation. Yet, Betelgeuse defies this expectation. Observations indicate it's rotating at about 5 kilometers per second, much faster than what should be possible for a star of its size and mass. This discrepancy suggests that something extraordinary is happening with Betelgeuse. To put this into perspective, consider other red supergiants. These stars typically rotate very slowly. For instance, Antares, another well-known red supergiant, has a rotational speed measured in fractions of a kilometer per second. This is what we would expect based on their immense size and mass. So why is Betelgeuse different? One of the most compelling theories to explain Betelgeuse's rapid rotation is stellar cannibalism. This dramatic-sounding phenomenon occurs when a star in a binary system strips material from its companion star, gaining mass and angular momentum in the process. In the case of Betelgeuse, astronomers propose that it may have once had a companion star in close orbit. Over time, Betelgeuse's immense gravitational pull could have drawn gas and material from its smaller neighbor. This influx of material would not only increase Betelgeuse's mass, but also impart significant angular momentum, speeding up its rotation to the rates we observe today. The evidence supporting this theory comes from the star's unusual rotational speed itself. For a star to spin at 5 kilometers per second despite its vast size, it must have acquired additional angular momentum from an external source. A close stellar companion provides a plausible explanation. Another piece of supporting evidence is the mass and chemical composition of Betelgeuse. Stars that undergo cannibalistic interactions often show unusual chemical signatures in their spectra, revealing the mixed material from both stars. Detailed spectroscopic analysis of Betelgeuse could uncover such anomalies, providing further support for the stellar cannibalism hypothesis. Additionally, simulations of stellar mergers indicate that such events can lead to rapid rotation. When two stars merge or one star accretes material from another, the resulting conservation of angular momentum can cause the surviving star to spin much faster than it would naturally. This aligns with the observed rotational speed of Betelgeuse. However, while stellar cannibalism is a strong candidate, it's not the only possibility. Another theory involves the star's internal dynamics. Betelgeuse is nearing the end of its life, and the fusion processes within its core could be contributing to its rapid rotation. As the star burns heavier elements, the resulting changes in its internal structure might redistribute angular momentum, leading to increased surface rotation. Another intriguing hypothesis suggests that the observed rotational speed might be an optical illusion. This theory hinges on the star's turbulent surface and massive convective cells, which could create the appearance of faster rotation than what is actually occurring. Betelgeuse is known for its chaotic and dynamic surface, marked by enormous convection cells. These cells are regions where hot plasma rises to the surface, cools, and then sinks back down. Each of these convection cells can be hundreds of millions of kilometers across, covering significant portions of the star's surface. The intense heat and movement within these cells can cause localized areas of the star to move at high velocities, creating turbulent patterns that can be detected from Earth. When astronomers observe Betelgeuse, they use techniques such as Doppler shift to measure its rotation. As previously explained, Doppler shift affects the frequency of light waves emitted by the star. If a part of the star's surface is moving toward us, it appears slightly bluer, and if it's moving away, it appears redder. By analyzing these color shifts, astronomers can infer the star's rotational speed. However, the convective cells on Betelgeuse's surface could complicate this measurement. If a large convection cell is rising on one side of the star and sinking on the other, it could produce a Doppler shift similar to what we would expect from rapid rotation. This means that the measured rotational speed might be significantly influenced by these surface activities, rather than the actual rotation of the entire star. Simulations and models of Betelgeuse have shown that its surface is incredibly dynamic. The star's outer layers are not solid, but are in constant flux due to intense thermal and gravitational forces. These simulations reveal that convection cells can move at velocities comparable to the observed rotational speed, potentially mimicking the effects of rapid rotation. Furthermore, Betelgeuse is nearing the end of its life cycle, which exacerbates its surface turbulence. As the star burns through heavier elements, its outer layers become more unstable. This instability leads to increased surface activity, with massive plumes of plasma erupting and falling back, adding to the complexity of accurately measuring the star's true rotational speed. The idea that Betelgeuse's rapid rotation could be an optical illusion is further supported by observations of other red supergiants, which also display surface turbulence in convection cells. These stars generally rotate slowly, suggesting that the apparent high rotational speed of Betelgeuse might indeed be a product of its surface dynamics rather than an actual physical spin. Betelgeuse's current state raises many questions about its future, particularly concerning the potential for a supernova event. As a red supergiant nearing the end of its life cycle, Betelgeuse is expected to explode in a spectacular supernova at some point. This event could have significant implications for Earth and the wider galaxy. The timing of Betelgeuse's supernova is uncertain. It could occur within the next few thousand years, or it might happen tomorrow. When it does, the explosion will be visible from Earth even during the daytime, shining as brightly as a full moon for weeks. This will provide astronomers with a unique opportunity to study a supernova up close, offering insights into the processes that drive these cataclysmic events. The impact of Betelgeuse's supernova on Earth will primarily be visual and scientific. The explosion will not pose any direct threat to our planet, despite its brightness. At 650 light-years away, Betelgeuse is far enough that the intense radiation and shock waves will dissipate long before reaching us. In the wider galaxy, Betelgeuse's supernova will contribute to the enrichment of the interstellar medium with heavy elements. Supernovae are responsible for creating and dispersing elements such as iron, calcium, and gold, which are essential for the formation of planets and life. The remnants of Betelgeuse's explosion will eventually mix with other interstellar material, potentially giving rise to new stars and planetary systems. Looking ahead, future observations of Betelgeuse will be crucial in solving the mysteries surrounding its behavior. Advanced telescopes and space observatories will continue to monitor the star, capturing detailed images and spectra. These observations will help astronomers refine their models of stellar dynamics and better understand the processes leading up to a supernova. Moreover, continued monitoring of Betelgeuse's brightness and surface activity will help detect any significant changes that might indicate an impending supernova. Sudden increases or decreases in brightness, changes in spectral lines, and unusual surface patterns could all serve as precursors to the star's explosive end. Betelgeuse's future holds both exciting opportunities and profound scientific insights. Its eventual supernova will be a landmark event in astronomy, offering a front-row seat to the death of a massive star. Talking about special stars on the sky, after you click to subscribe to the channel, check out our latest video where we show real images deep into the sun through the lens of NASA's Solar Dynamics Observatory.